Bismillahirrahmanirrahim. Today we will discuss work, energy, and power. The first slide shows Newton carrying an apple with a weight of 102 grams, which represents 1 Newton. He's elevating the apple 1 meter. So as long as he's doing so, he created a 1 joule of work. You see, this energy is stored as a potential energy. So that it can be used as a mechanical energy if he leaves the apple. Kinetic energy definition is shown on the screen, and then we will not consider it very important during discussion respiration and cardiovascular system because it is very small. The first slide will show the first 5 points. First of all, the definition of work. Work is done and energy is expended. You see, 1 joule of work is done when the force of 1 Newton moves its point of application 1 meter. So we are moving an object, the force for only 1 meter in the direction of the force. So we must accomplish all these items to define what the meaning of work. The muscles shortening, of course, multiplied by their force can yield the work of the muscle. To show the work of ventilation during the inspiration, we will create or we will use a constant pressure ventilator as an example to try to calculate the work. So we have a constant pressure ventilator, and it has, of course, a weight, and it has an area and a volume of descent. Of course, whenever it descends, all this can create a force and this distance, you see. So simply speaking, the force equation equals, and then the volume can be calculated, and then we can figure out the end result that the work done by the ventilator is the pressure time volume. And this is the graph, rectangular stippled graph showing the pressure created smoothly, 0.6 kilopascal, creating a volume of half a liter. You can see from this graph. So whenever I want to calculate, I multiply, of course, the pressure, which was 0.6 times, of course, the 10 to the power of cubic 3 times I'm sorry, 10 to the power of 3 times the half a liter, which is being shifted to a meter, of course. So the end result will be 300 millijoule, which is equal to 0.3 joule. So this is the figure you ought to know in case someone asks you how much the inspiratory work yields. This shaded area on the diagram shows actually the normal loop of the inspiration expiration changing during the volume and pressure changes. Of course, energy is never lost. And I want you to, so that you know, you don't have to be mixed up between the different models we will discuss later on. The most important point is to notice that the energy of inspiration is used for 2 things. First of all, the first component, which is the potential energy, which is stored for expiration. And expiration is used to overcome the resistance. The second component of the inspiration is used to overcome the stretch of the elastic tissue and overcoming resistance. So we represent this figure by the syringe model, as we will be seeing later. So this is the model where there is the ventilator, constant pressure ventilator, and this is the pressure created by from 0 to up to whatever. And then this is the cycle system, and this is the resistance, represented the resistance of respiratory tract, and this is the elastic band attached to a plunger. This plunger is representing the diaphragm, and this is the pressure created inside the syringe, which is the lung. So we are resembling a normal inspiratory process, and we are removing the respiratory muscles regarding the chest wall in such a procedure. So it will create a graph that we'll be seeing now. This graph, of course, creates, of course, as we had said before, a pressure of 0.6 kilopascal and a volume of half a liter. This change of volume creates a CD line. This slope of the line represents, of course, the compliance, and this half an area, shaded area, represents the inspiration, and this one represents the expiration. So each of them is considered half of the total. I'm sorry. Work of expiration, of course, when the cycle system is open to the atmosphere, the pressure yields zero, and the potential energy is used by the muscles of respiration to induce what we call the expiration process. The model we presented before was talking about a controlled patient, but now we'll talk about a spontaneous breathing patient. Of course, we know that inspiration descends the diaphragm for such distance, and you can represent the normal respiration by also the syringe model, but at such circumstances, we have two plungers. I don't know how are they attached to each other. One of the plunger, they call the right side, it is represented by the diaphragm, and the other one is the left one is representing the chest tissue. They create a fluid in between, as if it is an interpleural pressure, and then of course the diaphragm is opposed. I'm sorry, the plunger is opposed by the plastic band, as you can see, and of course this is the normal resistance of the respiratory tract. So whenever I move the plunger to the right resembling respiration, I create of course a difference in pressure, as we see, from 0.8 kilopascal to 0.4 kilopascal interpleural pressure, and then we create the inspiration, and then we go smoothly to expiration. Of course, this inclination curve of the bowing of this expiration, whenever it's increased, it indicates the increase in the resistance of respiration, and this stipple area on the right represents, of course, the reserve of the potential energy used for expiration. We can see that the chest expansion is not mentioned much in this experiment. It represents around the 10 to 40% of the total tidal volume. Total volume, mainly, of course, mainly due to the diaphragm, and of course we include the scalene muscles and so forth in the process of respiration. After that, this slide will discuss the rest of the 12 points. First of all, the power of breathing. Power of breathing, this is the second definition you must memorize. It's the rate of working. So simply speaking, it is if it's the unit of it is called, of course, is what is joule per second. You see. So simply speaking, if I have an example of the respiration where the work was 300 millijoule. I'm time it by the 16/60 to get the joule per second, which is around 80 millijoule. 80 millijoule. In the example mentioned before, it represents only 10% of the mechanical work. So we ought to consider the total mechanical work as 10 times this one. So it will be 800 millijoule. You see, this is what is written. Of course, the 9 point will discuss the power of laminar flow and the power of turbulent flow. You see, the power is represented by E dot, you see, and this is laminar and this is turbulent. It's correlated to the square of volume, and here this is a flow, and this is the other one is correlated to the cubic of the flow. You see, where energy, of course, means pressure per volume, and power means pressure per flow. So these are the difference between the work of laminar and turbulent flow. Of course, hyperventilation increase the work of ventilation. This is the point mentioning the lung compliance as I'm sorry, the compliant time, the time constant, which is star. Equals to compliance time resistance, as we had mentioned this before in the previous chapter. Work of the myocardial contraction. Of course, the heart creates a pressure and collects the amount of volume in the left ventricle. You can see. The pressure increases in the left ventricle from 0 to 16 kilopascal, and the volume is being increased up to 60 milliliter. So if we multiply both of this, we'll yield 960 millijoule. You see, so this is actually the work of the heart. Of course, all this can be measured by casters, of course, or an sonograph can estimate the volume, and also angiography can also measure the volume. Of course, we can estimate also the power of the heart, as long we know the work of the heart, and we know that, of course, the rate of the heart is around 60. So whenever divide 60 of it will yield 1. So the end result that the power of the heart is around of the lead ventricle around 1 watt. 1 watt. You see, we can also estimate the power of the right ventricle. Know that the pulmonary artery pressure is 0.2, 0.4, and then we can yield 0.2 watt. So the calculation of the total of the work of the power of the heart will yield 1.2 watt. The efficiency of the heart with 15% of the incidence. Then the total, so the total energy requirement will be 8 watt. So the total energy, actually speaking of the heart, they want to say it's 8 watt from the total basal metabolic rate of 80 watt, which represent 10%. Of course, hypertension increases the work of the heart, definitely the power of the heart, and cirrhosis and so forth increases the work of the heart, which is, if not treated, will lead to heart failure. Thank you very much. for your attendance and patience. The most important points in this subject is to know the definition of work and power, and to know how much is the work done by the respiratory system and the cardiovascular system. والسلام عليكم ورحمة الله وبركاته.